Okay, so in this video, what we are going to be taking a look at is what does it mean for a molecule to be polar, and what is this polarity thing that people are talking about in relation to chemistry. And so to understand polarity, let's just think about something that has actual poles. So think about the Earth. The Earth has both a North Pole and a South Pole. But what does that actually mean? Well, it means that the magnetic field that comes out of the top of the Earth on one side is a little bit different from the magnetic field that comes out of the Earth on the other side. And you could also think about something like a magnet. A magnet is also considered to be polar because it has a north and it has a south. It has one side that's a little bit different from the other side. And so when we talk about poles, really all we're talking about is something that is different on one end than it is on the other end. And so a molecule is no different than a magnet or the Earth in the sense that it can also be polar. The only difference is in chemistry. When we talk about polarity, we're not talking about north and south. We're actually talking about being partially positive, which is what this little symbol means, is partially, not fully, but a little bit positive, and a little bit negative. The real difference is that in chemistry, our poles are positive and negative versus north and south. But really all we're talking about is having slightly different sides to the molecule. And this ends up leading to really interesting properties. But why does this exist? Well, this all exists because of a property that exists within elements that is called electronegativity. There's a few things in chemistry where I feel like if you really understand it, you don't need to memorize some things. You can actually just like apply a principle. And electronegativity is one of those things. Electronegativity is how strongly an atom pulls electrons towards it. And so some atoms are able to pull electrons really, really strongly. And some atoms are able to like not pull electrons very strongly, or actually are better just giving them away. And this all has to do with the property of electronegativity. This actually leads to the different forms of bonds that exist in a molecule. In a molecule, if you have two substances that are pulling on electrons the same amount, then what ends up happening is they don't end up pulling electrons any differently. So think of this as like a tug of war that's just a tie. Both of these atoms are pulling on the electrons. And as they pull on those electrons, it's actually making it so that the electrons don't get pulled to one side or the other. But now imagine two elements that have different electronegativities. One of them is going to pull the electrons more strongly. So that's like this substance B in the middle picture of polar covalent. Substance A can't hold on to electrons as tightly. So what's happening is substance B is actually pulling the electrons away from the other substance. Again, think about like a tug of war, and imagine a tug of war where you're not like completely winning, but you're like pulling the other person towards you a little bit. And that's what it means to be polar covalent. It means to pull the electrons just a little bit towards itself as an atom. Now, you can also have on the other end of this spectrum what is called ionic. An ionic bond we haven't really discussed a lot in this unit, but it is when one substance's electronegativity is so much stronger than the other substances that it actually pulls the electrons away from the other thing. So like a metal like sodium, its electronegativity is so low in comparison to chlorine that chlorine actually rips the electrons away from the sodium. And that means that sodium gets the full negative charge, not the partial negative, a full negative charge. Sodium gets a full positive charge, not a partial charge. And they stick to each other because they have such opposite charges of positive and negative. So they attract. This is the idea behind electronegativity and how it affects our bonds. And so that's what we end up dealing with. We are really only focusing on covalent compounds when we're dealing with polarity, because ionic compounds are always polar. They actually always have charges, and they are much stronger because they're not partial charges, right? They're full charges. So we're going to focus on a covalent compounds, non-metals bonded together. And to understand polarity, let's look at some examples. What we're going to do is determine if a substance is polar. And to do this, we have to do a couple of things. Number one, as you probably guessed, we have to draw the Lewis structure. So our Lewis structure for BCl3 has boron in the center and 3 chlorines distributed all around it. Those chlorines, now keep in mind, boron, B, is one of the exceptions to the octet rule in that it always gets 6 electrons instead of 8. Now that we've done this, let's take a look at the geometry of this. This is an electron group geometry of, well, you have 1, 2, 3 electron groups. That's going to be trigonal planar. Let's figure out our molecular geometry then. Well, the molecular geometry, there's no lone pairs around the central atom. The molecular geometry here is going to also be trigonal planar. Okay. Now, I don't have a model that I can use to build this, but keep in mind trigonal planar is totally flat, and it kind of forms that little like 3-dimensional, that like little triangle out of these things, but it's completely flat. Now, what we want to do is check to see if there is an imbalance in the bonds of these things. And to check that balance and to see if there's a change in the bonds, like to see if there's an electronegativity difference between these bonds, what we need to do is jump to our electronegativity chart. And so what we would do is look for chlorine, and chlorine is right here, and then we would look for bromine, and it is right here. And there, if you subtract those two, 3.0 minus 2.0, you get an electronegativity difference of 1.0. That's a pretty significant difference. So what you would end up getting is a polar covalent bond. And since chlorine has the greater electronegativity, what's happening is chlorine is pulling the electrons away from the center, and you're getting an abundance of electrons towards the outside of this molecule. The only thing is when we think about the geometry of it, you're pulling electrons equally all towards the outside of this molecule. And so as you do that, you actually don't get different sides, right? Imagine if the Earth had equal magnetic pull in all areas all around it. Well, you wouldn't know which is north and which is the South Pole according to like magnets. And the same thing here, you don't know which is positive and which is negative because the whole outside is negative. Because this molecule is the same all the way around, this molecule is non-polar. So the way that we usually describe this is we would say that this molecule is symmetrical. And because the molecule is symmetrical, it's non-polar. It means that all of these atoms are pulling electrons equally, leading to there being no difference on the outside of this molecule. So ultimately, it is non-polar. So that's one example. And to illustrate this a little bit further, let's look at a couple more molecules. So the molecules I want to look at is I want to look at CH4 and CH2F2. Now, I'm going to draw these very quickly so that you would see what they look like. And then we're going to talk about symmetry. And what does symmetry actually mean when we're working in 3 dimensions? So these are my Lewis structures. I'm just going to add my lone pairs. And if you're looking like on a sheet of paper and you're thinking about, are these molecules symmetrical? Well, on paper, yes. Right? Like, you would probably look at these and think, okay, I remember when I was in elementary school and we remember you got the little red mirror thing and you put it on top of things and you would see okay, is this symmetrical? Well, if you were to put that little red mirror here, it would look pretty symmetrical. If you were to put it here, that would look pretty symmetrical, even this way, in this way. But don't think about the Lewis structure when you think about symmetry. When we think about symmetry, what you need to think about is the 3-dimensional structure. So think 3D. So what I want you to think about is something that is symmetrical in 3 dimensions has to be able to be rotated to look exactly the same in every single rotation. So I built these 2 molecules, and first we're going to look at CH4. I'm going to rotate CH4 so that this atom here is going to move to this atom's position. And you're going to notice that as I do that, it looks exactly the same. If I make another rotation, it looks exactly the same. If I maybe rotate it a little bit differently, like that, it still looks exactly the same. So CH4 is considered to be symmetrical. And any molecule that has symmetry is considered to be non-polar. Now, CH2F2. Okay, I want to show you how we actually get this structure. It looks like this. Carbon in the middle, F's on the sides, H is at the top, but I'm going to move it this way. Now let's do that same rotation. I'm going to move this over here. It no longer looks the same, but I can actually rotate it again, and you'll see that it looks very, very different if we move those 2 things there. Because this molecule is considered to be asymmetrical, meaning that when I rotate it, it does not look the same in every rotation, right? That means it's asymmetrical, which tells us that this is a polar molecule. A great way to think about polarity, or sorry, not polarity, to think about symmetry, is to think about a mattress. This is like my classic example that I always give. Let's say you go to the mattress store and you just buy yourself a regular old mattress. Is that mattress symmetrical? Well, it is pretty symmetrical because you could rotate this end over there You could rotate this like that. You could actually flip this mattress, and then once you flipped that mattress, you could rotate it again. It's pretty symmetrical in most directions. So this mattress is considered to be symmetrical. But maybe you sleep on your side. Maybe the clerk in the mattress store is telling you, like, you know what would be really good for you is if you bought this pillow top mattress. Okay, if you don't know what a pillow top mattress is, it means it has like the little fluffy part on the top to make it a little bit softer. Okay, you could still rotate it this way, but you can no longer flip this mattress. You cannot flip a pillow top mattress top to bottom, which makes this less symmetrical than just a standard mattress. So we would call this asymmetrical. If this were an example of, let's say, like molecules, let's say our mattresses were molecules, well, this molecule would be nonpolar. Whereas this molecule would be polar. Right? And that should make sense if you think about it. Like, it's different on one side than it is on the other. And that's the whole idea behind being polar. If you are polar, it's different from one side to the other. Hopefully this makes the theory a little bit more understandable. And what I'm going to do in the next video is actually work through examples and show you how we decide if a molecule is polar or non-polar. Okay, so make sure you check into that, and then again, as always, do some examples, ask any questions. Thanks for watching.